Hello everyone, I am Antonio Baiano Svizzero and we are going to continue our tutorial, our lesson about computational acoustics with open source software, FEniCSx. So let's go. First thing, we are going to open the script that I wrote last time. If you don't know what I'm talking about, I'm putting here the link to my previous video and you can find it in the Undabit YouTube channel. So last time we were left with this script that basically had one normal velocity boundary condition on one phase that we called phase 2 here, and the output of such a script was to have a sound pressure spectrum and the sound field all over the domain. So we are going to add a surface impedance boundary condition that for now it will be constant in frequency, and its value will be rho 0 times C0, so the product between air density and air sound speed. If we want to add an impedance boundary condition, we have to add a surface integral here. So let's write it. It is plus in imaginary unit, so J times air density times omega times divided by our impedance boundary condition that is constant for now, everything times our trial function, which inner product is by the test function, times the ds operator that is pointing to surface 3. Just to recall, let's open Gmesh. Our previous work was airmesh.msh. Let's check only the 3D elements. This is our air domain, and if we go on tools, visibility, we can highlight our velocity BC surface, that is this one, and our impedance BC surface, that is this one. So you can see this number column that is just our element ID that we have to use in Phoenix. So we are using 3 for the impedance BC and 2 for the velocity BC. So let's quit. And this is it. Since omega was defined as a Dolphin-X constant, initialized with 0, we are sure that inside the frequency loop it is going to change for every frequency, and it will be updated to the current value of the computation. So let's stay with this code. Let's export the sound field as well, and a new pressure spectrum that we will call PMIC spectrum 2, since the old one, I renamed the old one PMIC spectrum 1. Okay, so let's run it and see what happens. You can see that it's solving the problem and exporting the sound field in XDMF format. We have a spectrum here, and as you can see, it's quite flat up to a certain frequency. I want to remember that we are not doing any mesh sensitivity analysis, and this is just a tutorial about how to use Phoenix. Once you have the tool ready to use, you can do what you just do in commercial software as well. I'm assuming that you know what to do with a FEM tool. So when you buy a commercial software, you just do your mesh sensitivity analysis, you know your tools, and this is just a free way to do the same stuff. And I want to add another detail that was pointed out in the comments in the last video. And I want to add another thing that was pointed out in the comments on LinkedIn last week. This is a dB spectrum, so it's a sound pressure level spectrum, and I have to be clear that this PMIC has to be RMS to be, scaled with this standard value, but I'm assuming that we don't know which kind of input this is. This could be also an RMS, particle velocity spectrum. This is not very common, it is not rigorous, and rigorously all these acoustic equation, all these Helmholtz equation should be about absolute pressure. So I should correct this formula to account that this is an absolute value and not an RMS value, okay? So let's go ahead and plot our two pressure spectra, the one without the impedance boundary condition and the other one with the impedance boundary condition. So let's go and create a new file. I will call it import and plot.py. The following script will import our CSV files and plot them as we desire. So let's use the load.txt, numpy load.txt function to do that. So let's import numpy. Then let's import the first object with this function. We have to give him also a delimiter type. Since this is a standard CSV file, our delimiter will be a comma. And we will do the same thing with the other spectrum. So let's call it E2 spectrum 2. So let's save it. Our frequency axis will be the first column of the imported file. So I will call it in this way. Since it's the same, we could also, don't import the frequency axis for each spectrum, but just in case we change our frequency range or our frequency step, let's, make it flexible. So let's import the frequency axis in both cases. Just copy that. And then we can create our complex variable, that is the second column, because just let's recall that our CSV file is made in this way. The first column is the frequency axis, the second one is the real part, and the third one is the imaginary part. So if we want to make the complex pressure by these columns, we have to sum the real part to the imaginary part times the imaginary unit. So this way. I hope to not do any mistake. Let's just change P2 instead of P1, and this should work fine. So we want to plot this, and we are going to import matplotlib just like the other time. I think that we can just copy this from the previous script. Let's copy this and let's make two lines for the two spectra. This is P1 and this one is P2. So let's see how it goes. Let's save it. Let's run it. So as you can see, we get the flat spectrum for the BC, the impedance BC, and the previous spectrum for the case where all the walls were rigid. So this is what basically you have to expect from this computation, this simulation, because when we put an impedance on the wall, the surface number 3 equal to the higher characteristic impedance, we are basically setting the field to be planar field. So if we want to confirm that the orange case, so the one with the impedance, is a planar field, so a planar acoustic field, we can visualize it in Paraview. So let's visualize the field in both cases in Paraview, and let's also animate it just to, make it easier to understand. Let's go. Let's open our case, and we are going to compare the same solution for both cases. So now we are in lesson 2 folder, and we will open like a frequency like 800 Hertz and we will apply to see the field. As you can see, this is pretty clearly a planar field, but the problem here is that we can just see a real pressure sound field and an imaginary pressure sound field. They are both planar, but let's animate it to see how it's working right now. So let's animate it with a programmable filter. Now that everything is set up, we can see that this is the pressure field in time domain. Let's put it in this way, and as you can see, the wave is being generated on surface 2 and it's being completely absorbed on surface 3, since for a planar wave the perfect absorption impedance is density times sound speed. Okay, just to be sure that everything is fine, let's do the same thing for the case where we didn't put any impedance boundary condition here. So let's import that. Let's go on the other folder, lesson 1. We will import the same frequency. So we are plotting the same frequency for a different boundary condition here. In this case, the surface here will be completely rigid. So let's plot it. As you can see, the real pressure is 0, while the imaginary part is the only one that is present. So let's animate this one. As you can see, basically the field behaves like a stationary wave. That is what you have to expect when all the walls are rigid. Let's animate again. So here, the wave is being generated here by the moving surface with the normal velocity boundary condition, but all the walls, even this one, are rigid. Let's compare to the other case, where the sound field, as you can see, is going through the surface tree. Let's rescale that. Let's compare it again, and this is basically with another scale what you see. This one is with the boundary condition, the impedance boundary condition. That's it. Okay, right now I want to just, make our example a little bit richer. Let's just add frequency dependent surface impedance. So instead of having this constant, let's say that we have an impedance spectrum that we computed or measured in our acoustic chamber, or maybe we computed it with a Delaney-Betzley model, Shampoo-Allard model, and Mickey model. So let's say that we have that. I am going to take an impedance spectrum that was computed with a Delaney-Betzley model. I don't remember which resistivity value was that, but I just want to show you how to take any impedance model and any impedance spectrum in a CSV format and put it into your simulation. So you can use whatever impedance spectrum you want after this tutorial. Okay, let's take it and put it into our working directory. Our file is called impedance.csv, and it's made in this way. So we have a real part column and an imaginary part column. Okay, and our spectrum is between 50 and 2000, so it should be okay, since our computation goes between 50 and 1000 with a frequency step of 5 Hz that is compatible with the same frequency step that this impedance spectrum has. So let's just add few lines of code here. So first thing, we have to initialize ZS, so our impedance, as a constant, a Dolphinix constant, just like omega and K0. Then we have to import our surface impedance spectrum. Just like we did with our pressure spectrum. So we can copy this line, and let's call this just I. Then we change the name of the file, that is impedance.csv. The delimiter is the same. Then we can retrieve the real part of the impedance, that is the second column, so one here, and then the imaginary part of the impedance, that is the third column. And we can define our impedance variable, our impedance array, just call it however you want, summing the real part plus 1j times imaginary part. Okay, then so we have this array, this function defined here, that is just what we imported from the impedance spectrum, that can be both computed with a model, as I said before, or measured in your laboratory or acoustic chamber or whatever it is. Nothing has to be changed here, and we have to, this is going to remain the same, but we have to add another line here where we update the value at the current frequency into the frequency loop. We have to add another line, that is ZS value dot value. It's equal to our function NF. Of course, this is quite a simple way. This is going to work until you have the same kind of spectrum with the same, starting point and frequency step. So there are more elegant ways of calling this, without messing up everything. But this is going to work for now. Let's run it. Of course we have mistakes because this is how coding works. Oh, I just made a mistake here. This is a capital letter. Okay, Scala type with capital T. Save and let's run it. It is computing, and so let's wait until it finishes. Now that it's finished, we can see that we have another spectrum where we have similar resonances, but they are quite lower in amplitude. So let's compare this spectrum with the other one. Let's go in import and plot. Everything is the same, but we have, oh no, okay, everything is the same, so just run this script, python 3 import and plot.py, and we can see what happened here. The effect of the surface impedance was a shift towards the left side of the frequency axis of the resonant frequencies. So let's visualize this field in ParaView. We can add it. Let's go in the lesson 2 folder. Let's import the same frequency. Let's apply and then let's animate it. As you can see, the wave it's still moving through the left part of the screen, but it's kind of slowed down by the impedance wall. Of course, this is because this surface is not perfectly absorbing all the incident wave. There is a reflection field here that is going to be added to the incident part, and this is the result. So anyway, you can play with this however you want, and this is it. If you liked this video, please tell me in the comments. If you want to know something more about computational acoustics with FEniCSx, let me know in the comments. If you want more courses and video like this, hit subscribe button and follow me on LinkedIn. See you on the next video. Thank you for watching.